I've started the recording. Now, before we go into the discussions for today, there was one interesting question at the end of yesterday or last day's lecture that was on Monday, that whenever we talk about an op-amp, so let's say you have a inverting and a non-inverting terminal, and then you have an output. And you know that if the difference between the voltages at the inverting and non-inverting terminal, if they are, let's say, difference voltage VD, at the output, you should expect A times VD, right? And again, we are talking about, let's say, AC gain here. If A is the AC gain, at the output, you would expect A times VD for the op-amp, right? Now, on the other hand, when we talked about virtual ground property, that is valid only if you have, let's say, a negative feedback. So, for example, this was one of the negative feedback circuits that you have already learned in the past. And also you have looked into this circuit quite a few times in the class already, right? So if your input is here, let's say your V in is at this point, your non-inverting terminal is connected to an AC ground. And then if this is R1, this is R2, we say that the gain at the output point, or basically V out, will be equal to V in multiplied with the gain. And in this case, the gain is minus of R2 over R1, right? That's what you have learned earlier. Now, there is an interesting question that if there is a virtual ground at the input, so which means that the difference between the positive and negative terminals at the input, which is VD, let's say, if that is equal to 0, so you're saying there is a virtual ground, so the difference between these two is 0. So whatever gain you have in the circuit, whatever gain you have for the op-amp, that multiplied with 0 should be 0, right? So why do we not see 0 at the output? Why do we see the input multiplied with a particular amount of gain over here? So that could be a little bit of a confusing question that, yeah, if my input has a virtual ground, why does my output has a finite value? Why is it not 0? Because 0 multiplied by anything should be 0. Now, whenever you have a feedback circuit, you should think of it in this way. The answer lies in this trick that for an open loop op-amp, so on the left-hand side, what you have is the op-amp in open loop. So an input voltage multiplied with your gain, that's basically your output. Now, for an ideal op-amp, remember that this is the equation for an ideal op-amp, right? For an ideal op-amp, what is A? A is equal to infinite. So for an ideal op-amp, A is going to be infinite. So if you have a small difference of input voltages, that would result in an infinite output voltage difference, or the output voltage itself will be infinitely large, right? On the other hand, in this case, what you do with feedback is you apply that formula for feedback, A divided by 1 plus A beta, where A is the feed forward path gain and beta is the feedback path gain. Now, in this case, even if your A is infinitely large, what you end up with is equal to, let's say you divide your numerator by denominator with A. So you have 1 in the numerator and denominator, you have 1 over A plus beta. Because A is tending towards infinity, for an ideal op-amp, your 1 over A is 0. So this will be almost equal to just 1 over beta. So as you say that, see that when you have the circuit implemented with a feedback, your gain itself has changed for the system. The gain is not infinite anymore. Gain is totally is a function of beta. It's not even a function of A anymore. Okay. Now, keeping that in mind, also something that interesting that you can see over here is that your gain is 1 over beta. Now, you have learned to solve this particular circuit using KCL and KVL, right? We have seen that in the class. You know how to come up with this minus R2 over R1, this kind of a gain as well. But also think in terms of the beta network. What is the beta network? That we are digressing a little bit, but also this is important. That's why I wanted to mention this over here, that if you draw the ideal op-amp circuit, so you have an open circuit at the input side. At the output side, you have this dependent voltage source. You do not have, because this is an ideal op-amp, the series resistance connected with this dependent voltage source will be equal to 0. And that's going to be your output VO. Now, part of this is getting fed back using this R2 resistance, which is connected over here. And then you have a resistance R1 connected to V in. Now, because we are looking at the Thevenin equivalent resistances, your independent voltage source at the input can be grounded. So if you try to find out what is the voltage drop at this particular node, so if you're trying to find out the beta factor, the feedback factor for this particular circuit, what is going to be beta? Beta is the factor or the portion of this output voltage that gets available at the input side between these two terminals, right? Now, because this terminal is an AC ground, all you're looking for is the voltage at this particular node. What is the voltage at this particular node? That voltage is going to be a voltage division ratio. So you start from this point, traverse your way back toward the input, right? So what is the voltage at this point? The voltage at the positive terminal or the inverting, let's say this particular node is going to be R1 divided by R1 plus R2. Right? And that is basically your beta factor in this case. So your beta is this particular factor, which means that your 1 over beta is going to be R1 plus R2 divided by R1. So if you look at the absolute value of the gain, as you see that there is some amount of approximation here. Why is there an approximation? Because you approximated that this is going to be 0. So here you'll see that the 1 over beta, so if we write down 1 over beta, that's going to be 1 plus R2 divided by R1. Now, assuming your R2 divided by R1 is much, much larger than 1, your 1 plus R2 divided by R1, that's almost equal to R2 over R1, right? That 1, let's say it's 1 plus 100. If R2 is 100 times more than R1, 1 plus 100 is almost equal to 100. So your 1 over beta factor, just from the feedback, you can say that that is your gain right now. Your 1 over beta is your gain. And if you look at the absolute value of 1 over beta is R2 over R1. That was the original absolute value of the gain that you had initially. Why is the negative? Why is the minus coming in over here? Because if you, that's again boils down to one of the questions that we got in the last lecture, that if you look at the op-amp, the feedback is at the negative terminal, right? So this should be your negative and this should be your positive. And if you consider that, you'll get back that negative sign. So it will not be R2 over R1, it will be minus R2 over R1 eventually, right? Because there would be your beta itself is going to be minus R1 divided by R1 plus R2. So your 1 over beta is going to be minus of all of this, which is minus of this, which is almost equal to minus of R2 over R1. So from the feedback factor theory, so you have learned the theory of loop gain already. So from that also you can find out that the gain of this system is going to be minus R2 over R1. It's again another method of showing how to calculate the gain by not applying KCL and KVL. If you do not do a nodal analysis, this is another way. Just from the feedback theory and the loop gain theory, you can find out the gain of the system. Just another method so that you know. So now the question was that was raised at the end of the last lecture is, why is my output not 0? Because at the input side, if I assume that there is a virtual ground property, so the differential voltage at my input is almost equal to 0. The reason why the output is not 0 is that the output in this case, when you have a system or when you have, let's say, other components around the op-amp, and those other components determine the gain of the entire system. So here, as you see, that the op-amp does not even determine the gain. The gain is determined by R2 and R1, the ratio of R2 and R1. Right? So because the op-amp does not determine the gain, the final output voltage is this much. This is what you see. But on the other hand, if you trace it back, so if you see that your output voltage is V in times minus R2 over R1, and that is the voltage at the input of at the output of the op-amp. Now, for example, the op-amp still has a gain A which is tending towards infinity. If this is an ideal op-amp, the gain of the op-amp is still tending toward infinity. And if A times VD, which is VD over here, the difference of the voltages at the input side, if A times VD is the output voltage, then you basically have infinite times VD equal to your V out. Your V out is a finite quantity, but that finite quantity is an infinite gain multiplied with VD, multiplied with the differential voltage at the input side. So when you have a feedback system, you should actually think from output toward input when you think about the voltages. So the voltage at the output is already fixed. It's already fixed by R1 and R2. It's not even dependent on the op-amp's gain. So if that voltage is fixed, and if the op-amp has an infinite gain, the input voltage difference for the op-amp is going to be zero, because a finite number divided by infinite number is zero. And that's another proof of the virtual ground theory, that when you have this feedback system operating, the VD, the differential voltage at the input of the op-amp, is going to be zero. If output is finite and gain is infinite, a finite output value divided by an infinite gain, that's going to be your zero voltage at the input side, which is exactly what virtual ground says, right? Any questions on this concept? That why the op-amp's output voltage is not zero, even if you have a virtual ground property, which means at your input, the differential voltage is zero. That's because your op-amp's output is already fixed by other quantities in the circuit. It's not fixed by the op-amp. And since the output is fixed and the op-amp's gain is infinitely large, op-amp's input has to be zero. All right. Okay, so in today's lecture, we are going to talk about the frequency response. And again, as we were discussing at the end of last lecture, that if we start from a very simple RC filter, let's say you have a resistance over here, and you have a capacitance, which will give you an impedance of 1 over SC. And this is your V out. If this is your V in, then the transfer function of this system, which is VO over V in, or VO over VI, is going to be 1 divided by 1 plus SRC. This is something that we have proved in the previous lecture. Now, you also know in the Laplace domain, S is equal to J omega, where omega is your frequency, or angular frequency rather, and omega is equal to 2 times pi times F. So this is J times 2 pi F, where F is the linear frequency and omega is the angular frequency. Now you can write this equation as 1 over 1 plus J omega divided by 1 over RC. Right? So S is equal to J omega, and instead of multiplying RC with S, you're just dividing it with 1 over RC. Now, for a RC circuit, you also know that there is a pole. There is a pole at omega is equal to 1 over RC. So the pole frequency, which is basically this point, if your x-axis is frequency and y-axis is the transfer function. So y-axis is the transfer function, which is same as VO over VI. So this is your transfer function, which is VO over VI. After a certain frequency, the value of the transfer function drops. And that certain frequency is equal to 1 over RC. How you can show that? From this equation that you already found. So let's just put omega equal to 0. So if your omega is equal to 0, that is, you are looking at 0 frequency. In that case, what is the value of the transfer function? Your numerator is equal to 1, right? Your numerator is 1. Your denominator is 1 plus j omega times something. And if omega is 0, you just have 1 over 1, which is equal to 1. So you have a gain of 1 at 0 frequency. And you know that for a passive circuit, the gain of 1 is the maximum gain that you can have, because there's no active element that is increasing the gain. So the maximum output that you can have is equal to the input for a passive circuit, for a passive RC. So you're getting that transfer function or that gain of equal to 1 when omega is equal to 0. So at very low frequency, you have the entire input signal passed to the output. And you can also understand it very easily just from the fact that the capacitor, for which the impedance is 1 upon SC, If omega is equal to 0, your S is equal to 0. So the denominator becomes 0 for the capacitor's impedance, which means that the capacitor has infinite impedance at 0 frequency, which is another way of saying a capacitor is open at 0 frequency. Okay. If the capacitor is open at 0 frequency, you basically have whatever input voltage for on the left side of the resistor, you have the same output voltage on the right side of the resistor in that case. On the other hand, at infinite frequency, if your omega is very large, let's say omega is equal to infinitely large. In that case, of course, the capacitor 1 upon SC, the impedance of the capacitor will become 0, right? Because you have 1 upon SC, your omega is becoming infinite, which means S equal to j omega, that is also becoming infinite. So your denominator is becoming infinitely large for the capacitor's impedance. So your 1 upon SC is 0, right? If your 1 upon SC is 0, the capacitor is virtually a short at infinite frequency. So as we discussed earlier, that impedance is just frequency-dependent resistance. So for a capacitor, you see that this frequency dependence, because the impedance is 1 upon SC, at 0 frequency, the capacitor is an open, at infinite frequency, the capacitor is a short. Questions?
Does that mean, like, in high-frequency circuits, like, say, microwave or radio, even, that capacitors don't have, like, are they not used for, like, filtering and much?
That's a great question, and you actually found the problem right. That at high frequency, for example, radio frequency, microwave frequencies, you may have heard of millimeter wave, let's say 30 gigahertz to 300 gigahertz frequencies. So in that case, what happens is that the capacitor is becoming a short. So that actually creates problem in your circuit, because whenever you have a short, the voltage drop across the short becomes 0, right? So you don't even get any voltage. That's the problem. So that's why in RF, millimeter wave, or microwave frequencies, capacitors become the biggest source of non-ideality. But at low frequency, for example, you do your labs at lower frequencies, kilohertz, maybe will go up to megahertz or so. At those frequencies, capacitors are effectively open. So they do not create any issues, because you'll get the full voltage across any open circuit anyway, right? Now, what that does is that at infinite frequency, this capacitor 1 over SC, that becomes a short. So your voltage, V output, becomes 0, right? Because what is the voltage drop across a short if the other end of the short is connected to ground? So this is ground, the other end will also get connected to ground. You'll effectively have 0 voltage across the capacitor at infinite frequencies. You get that from this equation as well. So at omega equal to infinite, your transfer function is going to become 1 divided by 1 plus j omega. Now, because omega is infinite, you have an infinity here. So 1 over 1 plus infinity, that is effectively equal to 0. So at infinite frequency, you have 0 as your transfer function. And at 0 frequency, you have 1 as your transfer function. So this is 1. At large frequencies or infinite frequency, this becomes 0. One other thing, before taking the question, I wanted to mention one other thing, is that when your omega is equal to 1 upon RC, when your omega is equal to 1 upon RC, what happens in that case? You see from this particular equation, if your omega is 1 upon RC, and that is something that you're dividing with 1 upon RC once again, your transfer function becomes 1 divided by 1 plus j, right? Because omega is equal to 1 over RC. So your omega and this 1 over RC term in the denominator gets cancelled out. So what you're left with is just 1 divided by 1 plus j. What would be the absolute value of this transfer function? You already know how to operate with complex numbers from your high school math. So the absolute value of this transfer function is going to be 1 divided by square root of 1 squared plus 1 squared coming from j as well. So that becomes 1 over square root of 2, right? Because you know that the absolute value of any complex number a plus jb is going to be equal to square root of a squared plus b squared. Okay? That's just from the high school math that you have learned already. So the absolute value of the transfer function is 1 over square root of 2. So that's the voltage value, because see, the transfer function is basically the voltage output divided by voltage input. That is 1 over square root of 2. What would be the power? What would be the power ratio? Output power divided by input power. As you know, power is square of voltages, right? Because power, you can represent it as V squared over R or I squared times R. So your voltage or current gets squared Along with that, you have a resistance quantity, but assuming that the resistance quantity is equal at the input and output, you can say that the power ratio between your output and input is square of the voltage ratio between your output and input, right? So if that is true, what is the power transfer function? That would be square of 1 over root 2, right? The power transfer function is going to be half. Now remember that you have a concept of half power bandwidth. So that omega equal to 1 over RC, that basically becomes your half power bandwidth or the bandwidth of this low pass filter. So whenever we talk about bandwidth, we talk about minus 3 dB point, which is 3 dB below the highest gain. So the highest gain in this case was 1. 3 dB below that, you have your half power bandwidth, because 20 log 10 of half is equal to minus 3 dB. So we already learned the definition of decibels. So 20 times log to the base 10 of half is equal to minus 3 dB. And that is the reason why this is also called the minus 3 dB bandwidth of the system. So minus 3 dB bandwidth, half power bandwidth, all of them are the same thing. Also, this is called a pole. Why is this called a pole? That, okay, if you look at the transfer function, so for example, there could be frequencies for which the transfer function could become, let's say, 0. Or there could be frequencies for which the transfer function could become infinitely large, right? As you saw over here. The frequencies for which the transfer function will become infinitely large, that is generally called a pole. On the other hand, the frequencies for which your transfer function becomes 0, that is generally called a 0. So in this case, your pole frequency is going to be 1 over RC, because if you put, there's another way of analyzing this particular circuit, that when your S equal to, or when your omega is equal to 1 over RC, then your J component, this particular component, so let me write that down once again. Let me clear some of this, right? So you have made a note, I'm hoping. So let me clear this part. So if you see a transfer function that looks like this, S minus A divided by, let's say, S minus B, S minus C. So this is let's say, a general transfer function in the Laplace domain. What would happen if your S becomes equal to A? Your numerator will become 0, right? So S equal to A, that's the reason why it is called a 0. On the other hand, what would happen if your S is equal to B, or if your S is equal to C? If S is equal to B, you will have a 0 in the denominator, which means that the entire transfer function will become infinitely large. Similarly, when S equal to C, same thing will happen. So S equal to B or S equal to C, those are called pole frequencies. And S equal to A will be called a 0 frequency for this transfer function. Question?
Do we see harmonics of like poles and zeros kind of play at all filters or not?
It can happen in certain scenarios, but right now we are only discussing first order filter, where let's say the pole or first or second order filter, in that case, you don't need to be worried about that. So this is the 0 frequency and the pole frequency. Now, if you go back to this particular transfer function and you represent it in this form, how would it look like? So you, of course, have to divide your numerator and denominator with RC to come up with this kind of equation. So your transfer function will become 1 over RC divided by S plus 1 over RC. So now, again, from here, you can say that if your S becomes minus 1 over RC, in that case, you'll end up with a pole, right? And that is the reason why we call this the pole frequency as well, in terms of the absolute values. Okay, so that's the basic about your poles, zeros, what would happen for a transfer function if you have a resistance in series with a capacitor in parallel, which will result in this kind of a low pass filter. Similarly, if you had a capacitor first, so instead of your circuit looking like this, if you had, let me clear this up. So if you first had a capacitor and then you have a resistor. So if I just reverse the location of the capacitor and resistor, what would happen in that case is that with respect to frequency, if you again plot the transfer function, and again remember that this is going to be 1 over SC, that's the impedance, this is R. If you plot the transfer function, it will look something like this. And that is a high pass filter transfer function. The previous one was a low pass filter transfer function because in the previous case, you are passing the low frequencies, but rejecting the higher frequencies. So if your circuit looks like this is R, this is 1 over SC, and your output voltage is always here, your input voltage is always here. Again, your output voltage is here, and input voltage is here. So on the right-hand side, the same graph will look like this. So this is a low-pass filter. X-axis is frequency, y-axis is your transfer function. And in both cases, the pole frequency or the bandwidth, or basically the cutoff frequency, which is here, will be equal to 1 over RC. And it will be 1 over RC only if this is omega. So instead of frequency, let's call our x-axis omega, which is the angular frequency, that is equal to 2 pi times f. And omega is going to be 1 over RC at the cutoff point or at the point where you have the half power bandwidth for both the low pass filter as well as the high pass filter. All right. Now, what is interesting in both of these cases is that, remember that the transfer function that we wrote for this guy was, so let me write that down again. So transfer function is 1 divided by 1 plus SRC. And in this case, the transfer function is going to be R divided by R plus 1 over SC. Right? Again, a very simple voltage division that you have learned in lecture 1. So this is going to be SRC divided by 1 plus SRC. See, this is a very small difference. In this case, your numerator has SRC. In this case, your numerator is 1. The denominator is same in both cases. But one results in a high-pass filter, the other one results in a low-pass filter. Why is the left-hand side a high-pass filter? Again, put your omega equal to 0 or S equal to 0. If S is equal to 0, this 1 over SC terms becomes 0. Right? Or sorry, S equal to 0, so your 1 over SC terms becomes infinitely large. So R divided by R plus infinity, that's what you'll have at 0 frequency. So that's why at 0 frequency, you have R divided by R plus infinity, which is equal to 0. On the other hand, at infinite frequency, 1 over SC will be equal to 0. So you have R divided by R, which means that infinite frequency, your transfer function will be equal to 1. And here, at 0 frequency, transfer function is 1. At infinite frequency, the transfer function will go to 0. And in both cases, at S equal to, or omega equal to 1 over RC, in both cases, you'll see that you'll have the half power point. That is, your transfer function will be 1 over root 2 in both of these cases, the left side diagram as well as the right side diagram. Question?
Can you say why it's 1 over but I would see how negative 1 over RC would make the denominator 0.
Right. So you're talking about, so frequency, you're talking about a negative frequency at which you have a pole, right? But there's no meaning of negative frequency, right? Frequency can, the lowest value that you can physically have for any frequency is 0. And that is the reason why for, and if you do the math, you'll see like the full analysis of the complex numbers, which we simplified here. You'll see that this will be symmetric across the y-axis. So there would be of course, there would be a pole at 1 over minus 1 over RC. but that means there is a pole at 1 over RCL. Okay, so one thing that I wanted to mention here is that in both of these cases, after the pole, for the low pass filter on the right side of the pole, and for the high pass filter on the left side of this pole, what you'll see is that the slope of this curve, how would that look like? So for example, we increase your omega or increase your S by 10 times after the pole. Let's say after the pole, you're moving in this direction and you're increasing your omega by 10 times. So your transfer function, which is 1 divided by 1 plus SRC, your S is equal to j omega. If your omega increases by 10 times, your 1 divided by 1 plus SRC, that term will also almost increase by 10 times, right? Because 1 is a very small quantity now. So let me write this down. So if your S increases by 10 times, and if your SRC is much larger than 1, then your entire transfer function increases by 10 times, or entire transfer function reduces by 10 times rather, because you have SRC in the denominator. So transfer function will reduce by 10 times. So you have a one-on-one relation here, that your frequency increasing by 10 times, your transfer function reducing by 10 times. So you have a one-on-one relation between frequency and the value of the transfer function. Similarly, for the high pass filter on the left side of this pole frequency, if your frequency reduces by 10 times, the value of the transfer function will reduce by 10 times. Now, 20 log 10 of 10, 20 times log base 10 of 10 is how much? That is equal to 20 dB. Because if you have a logarithm base 10 of the value 10, that is equal to 1, right? So 20 times 1, that's why I'm writing 20 dB. So if your frequency increases by 10 times, your gain reduces by 10 times. Another way of saying that is the slope is going to be minus 20 dB per decade. So minus 20 dB per decade is the slope of this filter. What is the meaning of that? That if you increase your frequency by a decade, that is by 10 times. If you increase your frequency by 10 times, your gain of the system will reduce by 20 dB. And 20 dB is equal to 10. Like in linear scale, the value is 10. In dB scale, the same value becomes 20 dB, according to the definition of decibel scales. So if you increase your frequency by 10 times, your gain is going to reduce by 20 dB. And that's why the slope is called minus 20 dB per decade. Similarly, for the high pass filter also, on the left side of the pole, you have a slope of minus 20 dB per decade. Now, why is this minus 20 dB per decade and not anything else? That is, again, comes down to the fact that if your frequency increases by 10 times, your gain reduces by 10 times. And that is because you have a single S in the denominator in this case. So you have a one pole system. You have a single pole system, which is also called a first order system. So this transfer function is a first order transfer function. If you have a higher order transfer function, second order, third order, fourth order, all that means is that you'll have more number of poles. So if you have 2 poles, it becomes a second order system. 3 poles, it becomes a third order system, and so on. And in that case, the effect of S is going to be multiplied. So in this case, the S was having a 1x effect, a one-time effect. If you had S squared, that will have a squared effect. If you have S cubed coming from 3 different poles, that will have a cube timed effect, right? So this minus 20 dB per decade, this is only true for a first order system. If you had a second order system, you will have minus 40 dB per decade after the second pole. And you'll have minus 60 dB per decade after the third pole if you have a third order system, and so on. So how would that look like? Maybe if I can remove this from the board. So let's just take an example of a low pass filter once again. So the first pole, you have a minus 20 dB per decade after the first pole. And I'm drawing a low pass filter once again. So your x-axis is omega, the angular frequency, y-axis is the transfer function. So this is the first pole. You may have a second pole, after which you may start seeing a more amount of slope. So instead of minus 20, you'll see minus 40. And then you might have a third pole if it is a third order system. Then you might see this falling faster, even faster. And that could be minus 60 dB per decade. If you have more number of poles, you're going to fall, or the transfer function is going to fall faster and faster. So from minus 20 dB per decade, it will go to minus 40, minus 60, minus 80, and so on. Now, we'll come back to this concept toward the end of the course question. So that's a great question. So generally, when you talk about cutoff frequency, you talk about the first pole, right? So the cutoff frequency for this system is just the frequency of the first pole, which is over here. So let's call it P1. And then you have the second pole over here, which is P2. You have the third pole here, which is, let's say, P3, and so on. The cutoff frequency or the bandwidth of the system is basically the frequency of the first pole. Because after that, the gain anyway is falling. It doesn't even matter. So if you want a fixed gain, you need to be on the left side of the first pole for a low pass filter. So after the first pole, you'll probably not even be interested. So for example, your op-amp's gain will drop at this point after the right-hand side of the first pole. So if you want to have a fixed amount of gain for the op-amp, what you're interested in is where you have a constant gain. Why are you interested in the constant gain? Because your, so let's say this is your op-amp, and I'm not drawing the two signals here, or maybe we can also draw, let's say one of them is just AC ground. If you're applying a sine wave at the input, you know that if the op-amp has a particular amount of gain, you'll see a sine wave at the output as well. And if there is a 180-degree phase difference, you'll see a 180-degree phase difference at the output. However, real systems may not always just have a sine wave, right? You know how ECG looks like. Many of you already know how ECG of a person looks like, right? So that might have some peak, maybe some other, a little bit of a fluctuation here. Again, a P wave, QRST sample, and then like this. So this is not a sine wave in real life. So if you want to amplify an ECG signal, which is again millivolt level, very small amount of signal, and you want to amplify it, you want your output to look exactly same as the input, just an amplified version. But what is the meaning of the signal looking like this and not a sine wave? You already know about Fourier transforms. I think most of you know about Fourier transforms, that any signal can be decomposed as a combination of multiple sine waves. Right? So, and they will be at different frequencies. So this complex signal, the ECG signal, will be a combination of many different sine waves. You can decompose it in that way using Fourier transforms. What that means is that you want to have the same gain for all those frequencies. Otherwise, at the output, you'll not have this. If you don't have the same gain for all those frequencies, your output will not look same as the input. Your output will look something very different. It will not look like an amplified version, but it would start looking like a very different waveform. So you want the same gain for all those different frequencies in real life, which you can only get over here. Because see, your x-axis is frequency, your x-axis is omega. You want a fixed gain. You don't want a varying gain with frequency. And that is the reason why in real life, you would always want to be before the bandwidth or before the first pole for the system. And that is the reason why the concept of bandwidth is so important. Any other question? Okay. So one other interesting thing that I want to talk about here is that if you had a single pole system, if you had a first order system, which means you have a single pole system, then you just have this 20 dB per decade slope, right? So let me draw it with a different color. So if I just extend this, it will cross your frequency axis at some point, right? And if your transfer function is given in dB, 0 dB is equal to a transfer function of 1, right? So 0 dB is basically 20 log 10 of 1. So if your x-axis is 0 dB point, then if you had a first order system, that is, if you have one pole only, and you are reducing the gain by minus 20 dB per decade after that first pole, you'll cross your frequency axis somewhere, at some point. That frequency is called gain crossover frequency, or GCF. Again, we'll come back to this later. Right now, you don't need to remember it. When we discuss op-amps, let's say toward the later part of this course, we'll come back to this concept later once again. So this is called gain crossover frequency, GCF. You also have a concept of unity gain bandwidth, right? Unity gain bandwidth. And you also have a concept of gain bandwidth product. Now, my question is to you is that are all of these same or different? Gain bandwidth product is just a multiplication of gain and bandwidth, right? So if you have a first order system, what would happen is that your gain is this much, your bandwidth is this frequency point, and after your bandwidth point, if you go toward the right side, if your frequency increases by 10 times, your gain reduces by 10 times, right? So your gain bandwidth product remains constant. Remember that for an op-amp, generally people say that the gain bandwidth product remains constant. And that is because you want your op-amp to be a first order system. Again, there are implications when it becomes a second order or third order system. We'll learn that later. But for now, let's just remember, you want your op-amp to be a first order system, because if it is a first order system, your gain bandwidth product will remain constant. If it is not a first order system, what would happen is that when you have the second pole, you'll start reducing your gain at a rate of minus 40 dB per decade. When you reach your third pole, you'll start reducing your gain at a rate of minus 60 dB per decade, right? So if your frequency increases by 10 times when you are in the minus 40 dB per decade region, if your frequency increases by 10 times, your gain will reduce by 100 times. When you are in the minus 60 dB per decade region, if your gain increases by 10 times, if your frequency increases by 10 times, your gain is going to reduce by 1,000 times, because minus 60 dB is 1 upon 1,000 in linear scale. So if you have the second pole or the third pole, the assumption that your gain and your frequency increase and the gain reduction will not go hand in hand. You increase your frequency by 10 times, your gain might reduce by 100 times or 1,000 times when you have the second or third pole. So if you want to have a fixed gain bandwidth product, if your gain times bandwidth, if you want that to remain fixed, you need to have this first order system. So your gain bandwidth product is going to be the multiplication of this gain and this bandwidth, and that will remain constant throughout this slope if this is a first order system. However, if this is a second or third order system, your gain bandwidth product, which is the multiplication of this gain and this bandwidth, will not remain same after that, right? After the second pole or third pole. Only in the region where you have minus 20 dB per decade, your gain bandwidth product will remain same, or your gain times frequency will remain same. However, the concept of gain crossover frequency is whenever you cross over this 0 dB point. So if you have a second order system, after the second pole, you draw this minus 40 dB per decade line, and maybe that will cross over the frequency axis here. So that becomes your gain crossover frequency. For a third order system, this will become your gain crossover frequency. So your gain crossover frequency can be very different from your gain bandwidth product. And the gain crossover frequency is also called the unity gain bandwidth, because at that point, your gain is unity. Your gain is equal to 1. That's why in dB scale, you're calling it a 0 dB. So again, the purpose why I wanted to discuss this is that you should not get confused between these terms, that what is gain crossover frequency, what is gain bandwidth product, and what are the implications if you have a first order system versus higher order system. If you have multiple poles, then of course your gain crossover frequency and gain bandwidth product will not be the same. But in your op-amp data sheet, you'll always see that you see the gain bandwidth product, and they'll mention the gain bandwidth product is constant. That means you want your op-amp to be designed in a way that it has one single pole and that's it. Right? When we actually design op-amps later in the class, we'll remember this, that we have to design an op-amp with one single pole. If there are multiple poles, it's not the correct op-amp, or it's not the correct design for the op-amp. All right. So with this in mind, the frequency response of the op-amp is going to be very simple. So we can probably finish this entire concept in the next 5 minutes, because we already learned about all of these concepts. So if you have a low-pass function, a single pole low-pass function, you will have a 3 dB bandwidth. And then after that 3 dB bandwidth, the gain will drop. And the gain will drop at minus 20 dB per decade, which is basically 10 times reduction in gain if you have a 10 times increase in the frequency. So your gain, that is going to be equal to A naught. Now, you might ask, what does the subscript mean, that A naught? That means what is your gain at zero frequency? A0 or A naught, that is the gain at zero frequency. When F is equal to Fp at your pole or at the location of your minus 3 dB bandwidth, your A, the value of gain, is going to be A divided by square root of 2. And after that point, you have a minus 20 dB per decade slope, which means you can write the gain as A0 times Fp divided by F. Because A0 times Fp, that's basically your gain bandwidth product. And that divided by F is basically how much away you are in terms of frequency from your bandwidth. So that would be the value of your gain. And as your frequency increases, the value of your gain will reduce. At F equal to Fp, you can still say that from here, from this equation, you'll see that you'll have a gain of A naught, but in reality, you have a gain of A0 over square root of 2. So this is just an approximation. That third term that you see, A0 times Fp over F, that is true if your F is much, much larger than Fp. If it is just a little larger than Fp, then of course it's the most accurate representation should be A naught over square root of 2 times Fp over F. Okay. One other important thing is, what is the phase? The phase is defined as tan inverse of the imaginary quantity of the real quantity. Okay. So tan inverse of the imaginary quantity over the real quantity. Now, if you go back to the original equation over here, which is same as the equation that we had written for the low pass filter. Remember that there we had written for the low pass filter, the gain was 1 divided by 1 plus SRC, right? And what was 1? 1 was the zero frequency gain. The numerator was the gain at zero frequency. So instead of 1, if you have a zero frequency gain which is higher than 1, that becomes your numerator over here, which is A naught. In the denominator, you have 1 plus j omega times 1 over RC. What is 1 over RC? That is the pole frequency. So this is equal to 1 divided by 1 plus j omega divided by omega p. Right? So this is the same equation that we had learned before. So 1 divided by 1 plus j omega divided by omega p, that is the full representation of the system when you have a bandwidth. When you do not have infinite bandwidth, you have a finite bandwidth omega p, and omega p is nothing but 2 pi times Fp. Omega is the angular frequency, F is the linear frequency. So this is the same equation. Your numerator has A naught, because at zero frequency, you do not have a gain of 1, you have a gain of A naught for an amplifier. And then in the denominator, you have 1 plus j times F over Fp, which is same as omega over omega p. All right. Now, if this is your equation, you can find out what is going to be the phase. What is going to be the phase of this A times, or A, which is a function of Jf. So the tan inverse imaginary quantity over real quantity, which is minus of tan inverse F over Fp, minus of tan inverse F over Fp, Why is the minus? Again, you have gone through complex number theory in high school. You know that if your imaginary and real quantity that you're interested in, if that is in the denominator, when you are talking about the phase, you get this negative sign. And then you have the tan inverse of the imaginary quantity, which is f over fp, divided by the real quantity, which is 1. So minus tan inverse f over fp is your phase. And that phase is going to be 0 degree when f is much lower than fp. It is going to be minus 45 degree when f is equal to fp, and which is equal to minus 90 degree when f is much, much larger than fp. So when f is much, much larger than fp, tan inverse minus tan inverse infinity is minus 90 degrees. When f is equal to fp, minus tan inverse 1 is minus 45 degrees. And when f is, let's say, very close to 0, minus tan inverse of 0 is 0 degrees. So any pole will introduce a 90-degree phase shift. That is an important concept to remember, that any pole is going to introduce a 90-degree phase shift in your transfer function. Just like it introduces a minus 20 dB per decade slope in the transfer function after the pole. Here, after the pole, eventually at the location of the pole, you'll have a 45-degree phase shift. But at infinite frequency away from the pole, you'll get a 90-degree phase shift in total. Okay. So let's stop here. In the next lecture, we'll start from this point.